Let me begin though by welcoming everyone to today's Design Expert New Users webinar. And the goal of this session is to help new users become familiar with design of experiment concepts and also to introduce StatEase Design Expert software for the creation and analysis of really multiple types of experiments. So by way of personal introduction, my name is Richard Williams, and I've been a StatEase consultant for roughly 6 years or so. But prior to that, I spent 38 years in the chemical industry in roles focused on product and process development and improvement. By training, I'm a chemical engineer with a business degree, and I am also a Six Sigma Master Black Belt. And what that means is I've had an opportunity to train and coach in product and process development tools throughout my career. In my experience, though, I feel that DOE has been underutilized for problem solving and process optimization. But equally, I think DOE should be the tool of choice to help us launch reliable products and processes from the very start. This is the idea behind quality by design, or design for Six Sigma. So over the past 10 or 12 years, I focused on providing training for product and process improvement tools. And so today I'm really happy to provide this webinar to get you started with design of experiments concepts. By way of warning though, this is a huge topic. We're only going to be able to scratch the surface in 1 hour, but along the way, we will give you opportunities and resources to further your journey. Okay, so with that, let's go ahead and begin. So to prevent audio disruptions, all attendees will be muted on the call. But during the webinar, if you have questions, there's in the GoToWebinar toolkit, there's a tab for questions. And if you type those in there, we have Sherry on the call as well, and she'll do her best to try to answer, questions that are answerable within the short time frame that we have. Beyond that, though, if you continue to have questions, please send them to stathelp@statease.com, okay? And we'll do our best to get you appropriate answers. And if you have Design Expert software, it will be helpful to provide the serial number so that we know that you're a client. The slides and a recording of this webinar will be posted on the StatEase webinar page within a few business days, okay? So you can review this if you like. So the goal here really is first and foremost to understand why we would want to consider DOE methods in the first place. Okay, what is there about this type of experimental approach that is superior, arguably superior to any other approach? We are going to introduce Design Expert by demonstration. We will actually do, in this short 1 hour, we will do 3 case studies of different types of designs. Okay, so a lot coming at you. So with that, we're going to give you an awareness and applications for the different design types, or at least a few of them. And we'll provide some next steps so that you can continue your journey. So with that, just to make sure that everything is working, if you could find the raise your hand tab in the attendees window and just let me know that you're out there and can hear the webinar. There we go. Okay. I at least have one there too, so that's encouraging. Thank you. So I will be using StatEase 360, which is the sister product to Design Expert. StatEase 360 has a few more advanced features, but really for standard DOEs, Design Expert continues to be a solid product for what we've done for quite some time. So. But I'll be using StatEase 360. So by way of agenda, the first thing I'll do is talk about DOE and help us understand, what's in it for me? Why do I care? What are the advantages? Then we'll do 3 separate experiments, a factorial design where we're going to try to look at what factors and interactions govern a process. So we'll see that. Then we will move into the response surface category where we will really try to optimize a system. And then we're going to give you a glimpse of formulation or mixture type designs, which really, there's a little bit of a twist to how mixtures need to be laid out. We'll show you why, and then we're going to get into making an ibuprofen timed release capsule. So we'll see how that works. Okay, so let's continue with this. So what's in it for me? Why do I care? Well, let's think in terms of processes for a moment. You know, something as simple as maybe baking cookies in the kitchen. And, you know, we're trying to improve the flavor of the cookie. Well, the idea here is we're going to have some controllable factors, things that we think from a process standpoint might impact the flavor of the cookie. There might be time in the oven or the temperature in the oven. Maybe the type of cookie sheet that we use, a categoric choice, you know, Teflon coated versus, you know, stainless steel, what have you, aluminum. It might be which oven rack do we use, another categoric choice. But whatever it is, we're trying to relate the controllable factors in our process to one or more responses. It might be the flavor of the cookie. It might be the texture. It might be the yield, right? We don't want to burn too many or undercook too many. So our game here is to lay this out so that we can relate the controllable factors to the responses of interest. But in the real world, we have noise factors. We have things that are going to confound that relationship and make it sometimes difficult to discover. We might, when we set the temperature in the oven, for example, we might set it to 350 Fahrenheit, but it might cycle, right? Maybe we have, it might range from 325 to 375. We might have cold spots in the oven. Those are the kinds of things that can mix up our understanding of the controllable factors in the response. If you're measuring the taste of a cookie, well, how do you do that? Well, it might be 5 taste testers and you're going to report the average score. Well, they might not be consistent. You might have measurement system error. So our job is to relate the X's and the Y's, but to do so harnessing statistics so that we can find that relationship and make sure that it's not simply the noise disguised as the controllable factor having an influence. We're going to discover that we can have more insight into the process if we do multi-factor testing. You know, oftentimes in school or in our career, we're told that you have to hold everything constant and only change one factor at a time. Well, we're going to challenge that, and we're going to suggest that we are, in a very carefully planned way, we're going to change multiple things at the same time, and then using some really cool mathematical principles, we're going to decode the whole story so that we not only understand the impact of each factor, but this whole concept of interactions. Well, what's that all about? Well, I'll get to the right tool here. So let's look at what an interaction is. So briefly stated, an interaction is when one factor, the set point of one factor, has an impact on the effect of another factor. So let's look at baking cookies in the oven, and we're looking at the yield, okay? Well, we're going to study temperature, low temperature and high temperature. And we're going to look at time, short versus long. So let's study the red line, or excuse me, the dotted line first, the short. Well, at low temperature with low time, our yield is off because we're undercooking some of the cookies, okay? And as we increase the temperature, we're fully baking more and more of the cookies, and our yield actually gets better. Well, let's look at the long cook time. At low temperatures, our yield is high, but as we increase the temperature, we start to overcook or burn the cookies, and so our yield decreases. So the overall story here is that the impact of one factor, time, the impact of that factor depends on the set point for temperature, right? It either makes it better or worse depending on the temperature involved, okay? That's an interaction, and that's something that cannot be discovered with one factor at a time experimentation. But that's one of the beauties of Design-Experts, is by taking advantage of some mathematical properties of the way these designs are carefully laid out, we can discover the interactions. Also, multi-factor experimentation is going to give us, more information, the fewer runs, and it's a more efficient overall process. And the statistics involved are going to give us confidence in the findings that we hold, right? So that's an important outcome, is that we discover the truth and we know it. Okay. So Design-Expert really gives all kinds of different designs that we can use. And once again, we're going to look at 3 of them in this brief webinar. But a lot of times we want to capitalize on what we call the SCO strategy of experimentation, where we may screen, characterize, and then optimize. So a screening design is when we might have a large number of factors. Maybe for baking cookies, you could imagine 20 different factors that you think could impact the flavor of a cookie. Ambient humidity, ambient temperature, the phase of the moon, whatever. You could build a whole lot of different ideas into what may impact the flavor of a cookie. And a screening design is going to help us identify the critical few with as little work as possible. Okay, so that's what a screening design is for. Characterization then would be, we're going to build on that, and we're going to understand the critical interactions involved in the system. And then you'll see what I mean in a moment but if you think the peak performance might be somewhere in the inside of the design space, and we'll explain that a little bit more, then you may want to optimize the system using a response surface design. Okay, and like I said, that'll become more clear later. So the process that we really look at to create a designed experiment, well, really any experiment, but certainly applies to a designed experiment, is first and foremost, make sure you understand what it is you're trying to study, right? Define the objective and make sure it's clear in the context of measurable responses. And then you, the process expert, needs to select the input factors to study. What do you and your team imagine could control the process? Then we're going to help you select a design. You get to do the hard part, conduct the experiments. We're going to step back in and give you some really cool tools to analyze the results, capitalizing on the statistics involved. We're going to look for residuals and abnormalities or outliers. Then we're going to interpret the outcomes, and we're really going to rely on graphical tools as much as possible, because they can, a picture's worth 1,000 words, right? So using graphical techniques, we can often discover a lot about the process. We're going to give you some optimization tools so you can optimize the factors for maximum desirability. And then we're going to recommend that you go ahead and test your predictive model by doing confirmation runs, right? So you found your optimal performance, now go prove it. And once you're there, it's a good time to celebrate. So let's look at a factorial demo. And again, a factorial is going to look at what factors drive a process and the relevant interactions in a system. So here we go. I'm a chemical engineer, so pardon my bias. We're going to look at a chemical system. We're going to find the conditions that maximize the yield of a chemical reaction. And we have 5 factors that the engineers believe might control this. We have feed rate, catalyst, agitation rate, temperature, and the atmosphere in the headspace of the reactor, right? There's the liquid level, and then there's a headspace, a gaseous phase in the top. Are we going to fill that with nitrogen, or is it okay to just run this whole thing in air? Okay, so we're going to find out. So the goal again is to maximize the yield, and we're going to look at the parameters for calculating powers. So this is something that in a broader class we would take the time to delve into a little bit. But let me just kind of simply say that the whole objective of this concept called power is to make sure that we are collecting enough data with our experimental approach that we can find what we're looking for, and to do so with statistical significance, right? So probably the number one error that I encounter when people try to run a DOE is they don't have sufficient power in their design. They don't collect enough information. So that applies two things. Number one, we know what we're looking for, and we're going to call that the delta Y. And what we're saying is any improvement less than this will be unimportant. So in this case, we're trying to maximize the yield of the system. Let's say it's currently running at 80%, and we want to make a material impact on that. Well, what we're saying is, if the impact of what we're finding is less than 3% percentage points in the yield, then we're not that concerned about it. We certainly want to catch the heavy hitters, and so anything above 3 we want to detect. And we're also going to have an assessment of the experimental error in the system, the noise. Okay, so if you did the same experiment 10 times and you calculated the standard deviation, that's an estimate of sigma that we'd be looking for. Now, we're not saying that's how you have to get that number, but if you were to do that, that's how you would calculate the standard deviation. So that's a much longer topic, but the whole point is we're going to look at the signal to noise ratio, the delta Y to sigma, to calculate something called power. And we're only going to use that to make sure that we're collecting sufficient data to do our experiment. So let's get in the software and see how we're going to do this. So let's open something up here. All right, so here's Statis 360, and Design-Expert looks quite similar. We're going to begin a new design. And here are the regular 2-level factorial designs. So this is the first design that we're going to do. This is our default screen, but notice along the left-hand side there are multiple different design choices that you could pick. Soon we're going to look at a responsive surface design, so we'll come underneath here and we'll look at central composite. We also have mixture designs, and we're actually going to jump right past mixture for our third example and come all the way to a combined design where we can look at mixture plus some numeric factors. The whole, we can, if it were cookies, you're not only making the time and temperature in the oven, but you're looking at the recipe. So it's a mixture together with process factors. But we're going to begin with regular 2-level factorials. Along the top of the screen, we have the number of factors involved, and along the side, the resulting number of runs that will be required. The diagonal white blocks are what's called the full factorial designs, where everything is tested in combination with everything else at their high and low levels. We have 5 factors in this design. So I'm going to click this 32 run design. Okay, so it's 2-level factorial with 5 factors. So it's going to be 32 runs involved. And that's what we're going to use for this first design. Let me call your attention, though, to right above it, there is a green design with 16 runs, so half as much work. What we're going to suggest to you is oftentimes these green designs will also get the job done if you're trying to characterize the system. Yellow might be good for screening designs. Red, by and large, we won't use those for anything. So I'll hit next. And this is where we begin to type the information in. So the first factor that we're going to study is feed rate. And that's going to be liters per, minute. And it's a numeric factor, and it will go from 10 to 15. Okay, and so we will go through each of our 5 factors, but I am going to jump to one that's already filled in. Cut to the chase here. So we have feed rate, we have catalyst, agitation. Notice this last one, atmosphere, that's a categoric factor, right? So I took the little drop-down menu here and made it categoric because it's a choice of a categoric factor. It's either nitrogen or it's air, okay? Now, I suppose in the real world, you could look at a blend of the two, but here it's just going to be a categoric choice of nitrogen versus air. We will hit next. This is where we put the delta Y that we said was 3. If we fail to, if a factor has an effect less than 3 percentage points on the yield, now we're saying it's okay to miss that. We're saying that the experimental error is 2. So the ratio of the signal to noise is 3 divided by 2. It's 1.5. And that's what feeds the power calculation. And here is the resulting power calculation. The blue boxes always give us the insight that we need to interpret a screen in Design-Expert. So power is reported at a 5% alpha level. Okay, power should be approximately 80% or greater for the effects you want to detect. Okay, so these are all above 80%. More is better, but these are at least hit the minimum threshold. And what we're saying is, given the amount of experimental error in the system, if a factor or interaction term gives us at least 3 percentage point impact on the yield, that we have a 98% chance of discovering that. Okay, so we're collecting enough data in order to find what we're looking for. That's power. Then I'll finish the design. And here it is. The design is in random order. Okay, so, and that's an important concept with DOE, is we want to run them in a random order. And to make a long story short, that's going to be a protection against what we call lurking variables, things that will change or potentially could change through the course of time. Imagine that this reactor system, warms up through the course of time and it doesn't behave the same way start to finish. Well, we don't want to confuse the effect of that lurking variable with one of the factors that we're trying to study. And our protection against that is to randomize the runs. Okay, now let's get some data, and I have an easy way to do that. So I will simulate the data. This one is going to be Reactor, and there's our data. Once we have the data, we're going to analyze it. So we come on the left-hand side, we come down to the yield. We start the analysis, and we're going to present, this is stat ease now, right? So we're going to present some very simple yet very powerful techniques to help us decide what factors are important. Mathematically speaking, what factors and interaction terms belong in the predictive model that we're trying to create. The red line is the software's estimate of simply noise in the system. In each one of these squares on this graph, let me just right click on the first one over here. Each one of these squares is a factor in our study, or let's see if I find one, or an interaction term. Here's the DE interaction term. Okay. So if the red line represents noise in the system, what we're looking for are these squares that pop off that red line. So I'm going to make a selection that looks about like that. In here, we can see that factor B, the catalyst, matters. Factor E, atmosphere, matters. D matters. And we also have two factor interactions that are present in the system, and they're fairly significant. They're significantly off that red line. This would not be discoverable with a one factor at a time experiment. So we'd miss a good part of the story without using a designed experiment. Once we have selected the factors that belong in the model, we're going to look at the analysis of variance table, the ANOVA table. And here, if we had more time, we'd explain in glorious detail. But the key for now is look at what's in the blue boxes to understand what we need to know. The model, F value, is statistically significant, meaning it has a p-value of less than 0.05. Okay. The p-values for each of the factors involved are also less than 0.05, and therefore all the model terms that we've selected using the graph, they are indeed statistically significant. On the right, we have fit statistics, things that are, we understand. We have standard deviation of our predictions. We have the R-squared value, the adjusted, some other, nuanced versions of R-squareds. And the annotation gives us insight to what we're looking for. We want to see the adjusted and predicted be within 0.2 of each other. They are. We want to see the adequate precision be 4 or greater. It is. So we're in good shape. Then we're going to jump over to the next tab, right? We're moving left to right here. So we're going to click on the Diagnostics tab. In here, we want to find out if there appears to be anomalies in our data set. The first tool that we like to use in the upper left is the normal plot of residuals. If our predictive model has captured all the significant factors in the model, then there shouldn't be any signal left in the data set, and the residuals, the difference between the predicted and actual, should be just random variation, and they should fit a normal probability plot. And here they do. We also want to look at the predicted versus actual in the upper right. Okay, so ideally, we don't want anything outside the red lines. We also don't want to see a big megaphone shape on that plot. Okay, that would be, we wouldn't want to see something like that here, right? And on the normal plot of residuals, we wouldn't want to see a big S-shaped curve like that. So those would be bad things. We have the predicted versus actual. We want to make sure that makes some sense. We wouldn't want to see like a big strong C shape or something like that, where we're under predicting, over predicting, and then under predicting again. That would be a bad thing. So in this case, it's all good. The only time that we would look on this lower right-hand side is if we had some concerns with these other charts, and then that would help us understand how much influence those potential anomalies are having in our system. Okay. So let's see, erase all drawings, and let's come back here. All right, so we're good now. So then we're going to get into the model graphics. And here's where we can begin to see the overall story. This is an interaction plot. Remember, if I look at the ANOVA, I had two-factor interactions, BD and DE. So they have a letter in common, and E was a categoric choice. So if I look at the BD interaction plot and I toggle factor E, I'll be able to get an idea what's happening. So this is the BD interaction. Okay, and I can look at nitrogen. That's the chart with nitrogen. So let's just make sure we understand what's happening here. The temperature is 180, so the higher temperature is the red line. The lower temperature is down here, so it kind of looks like we're going to like higher temperature, and it also looks like we're going to want the higher catalyst level. But now I want to look at the difference between nitrogen and air. Everything degrades if I run this in air. So apparently oxygen perhaps is having a negative impact on my yield. So we know we're going to want to run this in nitrogen. If I click on the predicted value on this value here, we can see it's called a pairwise comparison. And now against that reference points, we can see that all these other conditions are indeed statistically different. These whiskers, specifically, they're called least significant difference. They don't cross the reference point, and therefore we know they're statistically different. And we have a prediction. Our yield would be 93.6 if we ran those conditions on average. Okay, so that's our estimate for what would happen. So we ran our DOE and we solved it. And here we go. We can use the graphical methods to take us there. So a full factorial tests all possible factor combinations. You can characterize all the effects, main two-factor interactions, and in fact, you can characterize everything all the way up to a five-factor interaction, and we had 5 factors here. But we could look at that, even though probably anything beyond two-factor interactions are quite unlikely. Certainly 4- and 5-factor interactions are quite unlikely. We also notice that the power assesses the probability that the experiment is going to help us discover what we're looking for. Okay, and we'd like to have power at least 80%. You know, if we absolutely need to make sure we're not missing anything, we may push that up to 95 or so. We don't want to run too few, and we generally don't want to run too many. It's expensive and difficult and time consuming. So we want a right-sized experiment. I mentioned that there was a green design just above the full factorial. So maybe we could have done this study using that design with only 16 runs. And that's a good idea to consider. And the green designs will help us understand main effects and two-factor interactions, not so much three-factor interactions or higher, but three-factor interactions are very rare, and 4- and 5-factor interactions are, basically you can say they don't exist. So this may be a very good experimental choice. Had we done the 16-run design, we would have discovered the power was going to be only 77% instead of our 80, and we'd have to make a decision. Quite honestly, I would probably have run it in 16 runs, depending on how consequential it would be of missing some of the lesser effects. All right, so that's a factorial design. Next, let's imagine that we want to take this up a little bit, and we actually want to optimize within the interior of the design space a bit more carefully. That's where, that's the domain of response surface systems. So let's take a peek here. If we have two factors and we're looking at a response, a two-factor interaction really is only going to allow us to provide a twist to the response surface plane, okay? A two-factor interaction or even a three-factor interaction, you can't create a hill or a valley within the design space, okay? So with a factorial design, we're only looking at the corners of the design space, the cube where we're studying, if you will. We're only looking at the corners. We don't intentionally put anything in the interior. Well, if we think that we have curvature or a hill or a valley within the design space, we're going to need higher order terms, in this case, square terms or quadratic terms, in order to create a hill or a valley in the interior of the design space. And now we will need to intentionally put some data points on the interior of the design space. So this little picture in the top is what's called a central composite design. And let's just kind of talk about the three different kind of points that are in it. The blue points are going to be the factorial points, just like we did in the previous case study. Okay, in the previous case study, we had three factors. Everything was tested in combination with everything else at its high and low level. Those are the factorial points. But now we're also going to put we're going to study generally multiple center points. So we're going to look at that point directly in the center of the cube, and we'll probably repeat that or replicate it a few times, 4 maybe 5 times, because we want a very precise estimate for what's happening there. Then we're going to do these axial points, which ideally will be outside the face of the cube, okay? So the cube is the design space, the region within which we want to make good predictions, but by putting some points outside the cube, it'll help us create a better mathematical model. If we have to, we can move those points to the face of the cube in order to make it more practical. For example, if I'm studying catalyst and the axial point was going to be at -1 part per million or -1% or something, well, I can't do that, can I? So I'm going to have to change that, and I'm going to have to move the axial point to the face of the cube. Okay, so let's jump into this. So we want to find the conditions that maximize the conversion, but we also have a second property called activity that we want to maintain within a target range. In here we have 3 factors, all of them numeric: time, temperature, and catalyst. Our goal, we want to achieve greater than 80% conversion, and we want to hit target a value for the activity of 63, but it needs to be at least 60 and no higher than 66. So let's see what we do. Okay, so here again is a restatement of the goals. So let's go ahead and jump into the software and see if we can't figure this out. If I get the right one, it's going to be better. Let's see here. Okay, so on the left-hand side, we're going to do a response surface design. So we're past the factorial designs that we saw before. We're going to come all the way down under response surface. It's a central composite. In here, I have 3 numeric factors: time, temperature, and catalyst. Okay, I've already typed that in. We're going to use the default designs when we can, and that's what we're going to do in this case. I have 2 responses this time. The first example, we only had 1 response, but now we're going to have 2, and I want to be able to satisfy both of these conditions. I will finish the design. And now we have a central composite, and I can just kind of take a look at this. My central composite has 3 different kinds of points. It has factorial points, center points, and it also has, these axial points. Okay, so I have 3 different kinds of points building this up. I will get my data, which for me is easy. And this will be the reaction. Now I have data. Well, once we have our data, we're going to come underneath analysis. This time I have to do two separate analyses, one for each of the responses that we chose. So let's take a look at conversion. I'm going to start the analysis. Okay, this is where things begin to differ between the factorial and the response surface. In the factorial space, we want to find the factors and interactions of significance. But now what we're trying to do is find a mathematical model that maps most appropriately to the data set that we have collected. A little bit different task. We're going to look at a quadratic. That's what's suggested. So I'm going to go ahead and click on that. I'll look at the ANOVA. I have a significant model, right? The blue boxes are again telling us what we're interested in. So I have a significant model. I have a not significant lack of fit. Well, because we did some replicates, specifically that center point, we're able now to break the residual into two components. How much variation I have when I try to do the same thing over and over again, the center points, well, that's called pure error. And everything else is a read on how well the model fits the data set. Well, we want our models to fit. Therefore, we don't want significant lack of fit, kind of statistical double talk. Anyway, this is the desirable condition. We want a not significant lack of fit. So we're good. And we look at our fit statistics. We have, it meets all the testing criteria in the blue box. So we're happy. Once again, we'll look at the diagnostic plots. And let's imagine that I thought, well, you know what, this data point right up here in the normal plot of residuals seems to be a little bit off that line. I wonder if I care. So we're going to follow that. If I look at that data point in the it's over here in the residual versus predicted, well, it's not outside the red lines, so I'm okay there. Let's take a look at the predicted versus actual. Well, it's a little further off the line than the rest, but okay. Do I care? Well, okay, so let's imagine that point perhaps is a little bit anomalous or something a little bit unusual. Now I want to look at how influential it is, and I'll typically look at a couple of charts in the bottom right. I'll look at the Cook's distance. Well, that data point is buried right down here, nowhere near the red line, so it passes that test. And then I'm going to look at the diffits, that difference in fits if I include or exclude that data point from the analysis. Well, that point is between the blue lines, and it's kind of, no more damaging, if you will, than anything else. So we're going to reach the conclusion that even if that particular data point were in some way an anomaly, an outlier, what have you, that it's inconsequential to the model. And so we're just going to move forward, accepting that data point is just a little bit, off compared to the other ones. Then we're going to look at model graphics there. And let me just show you the 3D surface on that one. And actually, I think the most interesting one, if I'm not mistaken, is going to be the BC one. So here you have the response surface. You can see we have a lot of curvature going on. And if I slide the other factor involved, the time, you can see that changes the shape of that curve. There's an awful lot of interesting behavior taking place between the three factors involved in this study. Okay. All right, so let's take a look at activity. We'll do the same thing. We will start the analysis. This time, a simple linear model is suggested, so it's not complicated at all. Okay, so I'll look at model here. We'll look at ANOVA. And this one's interesting now, is we have a significant model, not a significant lack of fit, but the temperature, the p-value is much, much greater than 0.05. Okay, and I want to take a look at the predictive capability of this model. It's 0.9276 is my predicted R squared. So the predicted R squared helps us understand how good this model would be at making predictions for future cases, for new data that I would be collecting. So this particular term, temperature, might not be statistically significant. So what happens if I take it out of the model? So I'm going to double click it, remove it from the model. I still have a significant model, not a significant lack of fit. The predicted R-squared, instead of 0.927, it's now 0.93. Okay, well, is that a big change? No, but the point is it didn't make it any worse. So I have a simpler model that maps to my data very well. So I will capitalize on the principle called parsimony, and I will use the simplest model that explains my data set. Okay, so I'm going to keep temperature out of it, and I actually have the best predictive model that I can from this collection of data. I'll look again at the diagnostics, and I'm happy here. And then we can just kind of look at the model graphs, and it's a linear model, so it's quite simple. But the goal of this one now is to optimize against the two properties of interest. So we're going to come down to the optimization module. And here I'm going to look at my two properties, conversion, and what did we say we want to do with that? Well, we want to maximize it. We want to make sure that we achieve at least 80%. And I suppose if we could get to 100, that would be the ideal condition. This little ramp on the bottom kind of shows you the what's called the desirability. So we won't see any solutions until we get to 80, and then it's going to be better and better and better as it chases up to 100. Okay. The activity, we have an interesting property there. We actually want to target a particular value. We want this to be 63, but we don't want any solutions that don't achieve at least 60 or go above 66. So this little ramp on the bottom, it's going to preferentially target 63, but it won't accept any solution with less than 60 or over 66. So as we put those two goals together, we have a solution. Right, so time, temperature, and catalyst, as indicated on these ramps, will deliver a conversion of around 97% and pretty much nail the activity goal that we had in mind. Okay, so a response surface to find the optimal conditions. We had two different responses in this case, and we created models for both of them, and then simultaneously solved for the best solution that achieves the goals that we set for each of those. Now, there are a lot of other bells and whistles in this optimization module, and you know, a little bit fuller course rather than 1 hour intro, and we would showcase quite a bit of the tools involved with the optimization. Okay, so response surfaces are useful when we think we have curvature or nonlinearity within the design space, within the cube, if you will. The model terms are going to be quadratic or higher order to be able to create the hill or the valley within the design space. The disadvantage for response surfaces is that they will require more runs than factorials. Okay, so you have more insight, you're better able to optimize, but you're collecting more data, right? So there's no free lunch in this world. We have numerical and graphical optimization tools to find the optimal conditions, in this case with two criteria, but you can simultaneously solve for as many criteria as you have. Now, if what we've talked about so far is an area of interest, working on processes in particular as opposed to formulation, then you may be interested in our modern DOE for process optimization. If for an individual, you can sign up for a public course, which is, I think for that one, well, I'll show you in a moment, but several half-day sessions online. For groups, for say a single company has 6 or more people, we can conduct a private course at your location. Okay, if you want to learn more, you know, staties.com or contact workshops at staties.com. But here's a little bit of an update on that story. We have our public DOE training. We now have something called the essentials courses that we're offering, which are a little bit different than the comprehensive course that I just talked about, the modern DOE for process optimization, which is 5 half days. These are a little bit more bite-sized and might meet your needs specifically a little bit better. Each essentials course is 2 half days, and we offer 4 of them. The foundations for DOE, factorial, fractional factorial for process development or response surface. So I suggest that if you're interested in process type work, that you consider these essential series courses. The last one here is going to be for formulation work, but also, trade that off against, in your mind, the full 5-day course where we might get into a little bit more detail. Okay, so different product offerings if you want to go beyond the 1-hour webinar. Okay. Mixture designs. Okay, so mixtures are a form of response surface designs that are tailor fit to work within the formulation world. Okay, so they're a little bit, there's a twist to it. And at the end of the day, the factors are ingredients of a mixture or a formulation. Okay, and really the response is a function of the proportions, not amounts, right? If I'm making cookies in the oven, I'm looking at the cookie batter. The amount of sugar, the absolute quantity of sugar that I put in the recipe doesn't matter. It's the proportion of sugar to flour. It's the proportion of, sugar to water, whatever the ingredients are. It's the proportions that really drive the characteristics. Okay. So for example, if we used a factorial design to make lemonade from lemons and sugar water, well, I would study everything at its low and high combination. So, 1 to 1 in the bottom left, 2 to 1, 1 to 2, and in the upper right, it would be 2 lemons to 2 glasses of water. But wait, that's the same formulation, isn't it? That's the same formulation as the bottom left, right? So if I try to do a factorial design, I've got a built-in problem because I'm really doing the same experiment twice. I'm just accidentally using this, well, it won't work. So we need to take that into consideration. If I have 3 factors, 3 ingredients, in a factorial design, I'm free to independently change all of the factors, time and temperature in the oven. Maybe the third one was, the oven rack. Okay, I could independently change all of those and study all combinations. But with a 3-component mixture, as soon as I know 2 of them, because it has to sum to 100%, well, I can calculate the third one. So I lose a degree of freedom, right? I have this constraint that I have to work into the story. So that's what mixture designs do. And they also give us some of the predictive polynomials that we use are better tailor fit to work within the world of mixtures. So let's get into one and see how this works. So we're going to do a mixture amount experiment. Okay, well, what is that? So like fertilizer, the impact of fertilizer might not only impact on be impacted by the composition of the fertilizer, but how much you use, right? So, and the third one, medicine. Maybe after this webinar, you'll have a headache and you want an Excedrin. So it will not only depend on the composition of the Excedrin, the amount of aspirin, acetaminophen, and caffeine that's in the tablet, but whether you take 1 or 2 tablets. Okay, so mixture plus amount. So here, what we're going to do, we're going to make an ibuprofen timed release capsule, and what we're going to do is we're going to put a latex coating on a ibuprofen tablet, and we're going to change the formulation within these ranges. So we have 3 ingredients, EA, MMA, and TEC to keep it simple. The 3 of them combined will be 31%, and then the other 69% would be something held constant, probably in this case water, since it's a latex coating. Okay, but we're changing within the 31%, and then in our laboratory mixer, we can inject anywhere from 15 to 25 mLs of coating into this laboratory tablet coating device. Okay, our goal is to find the conditions where we dissolve a certain amount in 1 hour and a certain amount in 12 hours, timed release. So We want from 10 to 30% with a target of 20 released in 1 hour. And in 12 hours, we want to target 90%, but it needs to fall within the range of 80 to 100. So how do we build that? Okay, well, we're going to come all the way down. Let me open these other ones so we see what's going on. Standard designs, mixture designs, response surface. So let me kind of open up the menu. So all the way down, we have the most flexible design possible called these custom designs, optimal / combined. We have 3 mixture components. We have 1 numeric factor, the quantity in mLs of coating that we're going to put in the mixer. I'll hit next. And here's the composition, the 31%. These are the ranges that we were given in the study, so we're happy with that. The numeric factor, the amount of coating used, well, that's going to range from 15 to 25, so we put that in. It's going to offer up a standard optimal design. An optimal design is where the computer is going to shop around for the best collection of data points to run to give us an effective study. So here we have a 28 run design by default, and we're just going to accept that for now. We have our 2 criteria, our 2 responses, dissolve 1 hour, dissolve 12 hours, and we'll finish the design. I will simulate and get my data. Then we need to analyze our 2 responses. And this is just the same as a response surface, but it's a little more complicated because we are not only looking at the mixture or the process factors, but the mixture as well. So it's going to recommend a design. We're going to take its suggestion. Now, remember in the last case study, with my eyeball, I recognized that I could take temperature out of the system. We're going to use an automated approach now, and typically with these more complicated designs, we're almost always going to do what's called model reduction. We're going to take some of the terms out because they are chasing noise, not signal. So I'm going to use this thing called auto select, and I'm going to use 1 or more of the different 2 options that I have here, and it will take some of the terms out. Then when I click on ANOVA, in this case, it's detected that I've taken too many terms out, and it wants to add some back to support what's called hierarchy. Long story short, we're always going to say yes to that question. And we've created a model, and it passes all the criteria that we've talked about. We can take a quick peek at the diagnostics, and we're happy with that. Then we'll do the same thing with our dissolve in 12 hours. Start the analysis. Come to model. I actually will do the model reduction again to eliminate terms that don't need to be there. I'll accept those. Come to the ANOVA table. There it is. So I've created a model now for my second response. Super. Okay, and I'll look at the diagnostics there. So that's all good. Okay, so I've created 2 models for our 2 responses in a optimal design where the computer has selected the appropriate data points for me. Now all I need to do is find the answer. So I'm going to put my 2 criteria in. Dissolve in 1 hour. That's another target. And here we want that to be, what we say, 20. No lower than 10, no more than 30. The little triangle shape on the bottom highlights what's going on with that one. The dissolve in 12 hours, we are going to target. This one will be 90, no lower than 80, no more than 100. And then we're going to hit solutions, and there it is. So here's the formulation, the first 3, right, on the ramp view. And then the amount of coating, 18. And if we create the tablet like that, we would expect roughly, let's round it off, 25% will be dissolved in 1 hour, and 87% will be dissolved in 12 hours. And that meets the criteria of interest. Okay. So mixtures have a built-in constraint. The formulation needs to sum to a total. It is an RSM design. It's used for optimization, but because of the constraints, special approaches are needed. And so we offer the mixture designs to take us there. Design-Expert can create custom or optimal designs that combine mixture and components and process factors. In this case, it was a simple one. We just included the amount of the coating involved. Okay, but it's a very flexible. The optimal designs are very, very flexible. If you have an interest in mixtures and formulation in your world, we would suggest taking the mixture design for optimal formulations course to advance your skills a bit more. There is also one of the essentials course is a two half-day version of this course that might be of interest as well. Doesn't really get into the combined designs too much, but will at least get you into the mixture world and help understand the differences in important considerations. So a DOE is a planned multi-factor approach to efficiently and effectively determine cause and effect relationships. Remember the little process box, the X's and Y's. The statistics provide power and credibility to the conclusions, right? So we can relate the X's and Y's in the presence of noise and know that we have found the statistically significant factors. Design-Expert software is specifically specialized for the world of design of experiments, and we give a wide variety of experimental types that you can use, whether you're using Statis 360 or Design-Expert. There are some books written by the Statis staff that are a little bit lighthearted, you know, in as much as you can be for something as potentially dry as statistics. But these are a fun-spirited way to help us advance our skills a little bit and to, you know, capitalize on the concepts that have been developed over the past century or so. We also have case studies that you can access by going to our website, www.statis.com. Look at publications, so those might be of help to you. There are some Stats Made Easy training available through YouTube. You can look at white papers, etc., and other publications at our website as well. The software itself has a lot of helpful information in the help screens and also the light bulb for context-sensitive information. So you get to a screen, you want to understand what you're seeing, click on the light bulb, and it'll give you some context-sensitive help as well. As I offered earlier, if you have additional questions, those can be sent to stathelp@statis.com. And that's it. So we encourage you to make the most of every experiment, harness the power of DOEs to get the most effective and efficient design possible to understand your system or formulation. So with that, I thank you for attending today's webinar. And again, if you have additional questions, please send them to stathelp@statis.com. I thank you for your attention. Have a good day.